Welcome! Today, we'll walk through a stiffness method for a very simple rod system. In the previous video we introduced a stiffness matrix for a rod element. The system consists of two rod elements, labeled 1 and 2, and three nodes, labeled 1, 2, and 3. Each element has a length, L, cross-sectional area, A, and modulus of elasticity, E. A force, P, is applied at node 1. First, we define the stiffness for each individual element. The stiffness for element 1 is K1, and for element 2, it is K2. Next, we create the element stiffness matrices, K1 and K2. Notice they are both 2 by 2 matrices because each element connects two nodes. Now, let's look at the entire system. Instead of considering displacements for each element separately, we define a single global displacement vector, U, for the entire structure. This vector contains the displacement at each of our global nodes, U1 at node 1, U2 at node 2, and U3 at node 3. The goal of the stiffness method is to find these unknown displacements by solving a system of linear equations. We express each element's stiffness matrix in terms of the global coordinate system. Element 1 connects nodes 1 and 2, so its matrix, K1, is a 3 by 3 matrix with non-zero entries only in the rows and columns corresponding to nodes 1 and 2. Similarly, element 2 connects nodes 2 and 3, so its matrix, K2, has non-zero entries only in the rows and columns for nodes 2 and 3. These equations relate nodal displacements and forces for individual elements. To obtain the relationship between nodal displacements and forces for the entire system, add these two equations. Since the displacement vector U is the global displacement vector, using the distributivity of matrix multiplication over addition we can rewrite this equation as follows. This gives us the relationship between nodal displacements and forces for the entire system. We add the expanded 3 by 3 matrices for K1 and K2 to get the final global stiffness matrix K. Notice how the term at the second row, second column becomes K1 plus K2. This is because both elements 1 and 2 contribute stiffness at the shared node, node 2. Now we define the final global load vector, F, based on the forces applied to the system. At node 1, a force P is applied in the negative x direction, so the force component F1 is equal to minus P. At node 2, there is no externally applied force, so the force component F2 is equal to 0. This is an application of equilibrium at the node, meaning the forces from elements 1 and 2 must balance. Finally, at node 3, the force F3 is the unknown reaction force from the support. We will solve for this force later. Now we can write out the full global system equation, Q equals F, using the matrices we've just assembled. Looking at this equation, we can identify our knowns and unknowns. The displacements U1 and U2 are unknown, but the displacement at node 3, U3, is known to be 0 because it's a fixed support. The forces F1 and F2 are known, F1 equals minus P and F2 equals 0, but the reaction force F3 at node 3 is unknown. This system of equations can be rewritten in the following form. Next, we apply the displacement boundary condition, which in this case is U3 equals 0. We can simplify the first two equations by moving the terms containing the known U3 to the right-hand side. Since U3 equals 0, the first two equations become. This new, simplified system can be written in matrix form as: if the prescribed displacements are equal to 0, then the system of equations for the unknown variables can be obtained from the original system by eliminating the rows and columns in the global stiffness matrix that correspond to the degrees of freedom with 0 displacements. You also eliminate the rows in the displacement and load vectors that correspond to these degrees of freedom. Now that we have the simplified system, we can solve for U1 and U2. We add the two simplified equations together to solve for U2. Solving for U2 gives us. To find U1, we substitute the value of U2 into the first simplified equation. Substituting U2 gives us. Solving for U1 gives us. After finding the displacements, you can find the reaction forces by going back to the original equations. F3 is the reaction force corresponding to the prescribed displacement U3 equals 0. From the original set of equations, the last equation is used to find F3. Since the displacement boundary condition is U3 equals 0, and you have already solved for the value of U2, you can substitute these values into the equation. In summary, the stiffness method provides a systematic approach to analyzing a simple rod system. We began by treating the rod as two individual elements. The first crucial step was to calculate the element stiffness matrices, which define the force-displacement relationship for each element. The next step was to assemble these individual matrices into a single global stiffness matrix. This global matrix accounts for the stiffness contributions of both elements at each node. With the global matrix assembled, we could then establish the global force-displacement relationship, relating the external forces to the unknown displacements. The key to solving this system was applying the displacement boundary conditions. By identifying the known and unknown displacements and forces, we were able to reduce the original system of equations down to a smaller, solvable system. Finally, we solved this simplified system to determine the unknown displacements. With those values, we were able to use the remaining equation to calculate the unknown reaction force.